you know that a linked list is dynamic, right? It's not restricted to a given size. You know, a linked list is everywhere. Like in computer science, it is not what is it called? It's not, you know, sequence. It's not on a straight line. It's not, you know, sequential, right? It can be everywhere. That's your linked list. Okay, so you can, you know, implement a queue using an array, or you can use a linked list, right? Good. But though, you know, linked list is dynamic, there's no, you know, size restriction, but there's also a trade-off, right? And your trade-off is space. Okay, that's the trade-off you have when you use a linked list to implement your queue. You have space, you know, restriction, because, you know, space is a limited resource, right? It is not unlimited. Okay, so you can apply queues in OS task scheduling, pooling, network buffering, web servers, BFA, that is your breadth first search algorithm, and simulation. So these are like some of the uses of queue systems in programming / computer science. Okay, let's go ahead. So if there's any question, you can also ask, right? When and why we use a queue? So when and how and why we use a queue, right? So we use queues when we need to process items in the exact order they arrive. That is your first in, first out. Okay, so if you want to, you know, process items in the exact, you know, order, when order matters actually, so you use a queue. And also when handling asynchronous data or task, example is our simple queue system like the SQS or the Kafka or the Rabbit MQs, you know, those are like when handling your asynchronous data task. And also managing shared resource fairly, buffering data between producers and consumers. Good. So why use a queue? You know, these ones are more of, you know, theoretical stuff. We'll get to the sweet part, which is the programming part, right? All right. So why use a queue? One is that it guarantees order and fairness, right? It decouples different parts of your system. You know, for example, your microservices. Efficient for sequential access and essential for many algorithms and reward systems, right? So I believe these are things that we can easily, you know, relate to it. For example, when order matters, you want to run a processing that the order matters. You want to decouple your system. For example, you have a user management system, you have an ordering system, and you want to decouple them, but while they are still communicating asynchronously, right? And efficient for sequential access. Good. And for many algorithms, for example, is our breadth first searches and you know, reward systems. So those are some of the reasons why you would want to use a queue. Okay, so we have discussed what a queue is and the different you know ways that we can, you know, implement a queue and when to use a queue and why. So here we have like the different types of queues, right? So the first one we have is the simple queue, which is our linear queue. We have the circular queue, the priority queue, and the deck, right? And this deck stands for double-ended queue, right? But for the purpose of this, you know, section, we'll be focusing more on circular queue and you know, circular queue. Okay, I didn't put it up, but we're focusing more on the circular queue part, right? Yeah, the circular queue part. Good. Though I will be looking into both circular queue and the linked list, you know, implementation of a queue, but these are just the types of queue that we have, right? And we'll just, you know, run over them quickly. Yeah, run over them quickly and see what they are all about. So first we have the simple queue. Okay, so this simple queue is also known as the linear queue. Okay, And how does it work? Elements are being added from the rear, which is the back, okay? Then they are being removed from the front. It's a straightforward system. Okay, the merit is it is simple to understand and implement, and demerit, that is the trade-off, is space waste. So you can ask yourself, like, how does the simple queue waste space? Though I don't have like a drawing system here to draw, but let's just look at this item here, right? Now let's just imagine, just use our mind eyes to picture. Okay, now for example, when this rear was here, you know that at the initial time, the front and the rear, they are all in this place, right? Good. So for every time you add an item, and for example, your array is fixed length, right? So for every time you add an item, the rear will increase, right? And for every time you remove an item, the front will increase. So the rear increases when you add an item, and the front increases when you will remove an item, right? Now let us say you have added an item up to this point, right? Yeah, to this point. Then you now start to remove. So for every item you remove, you move the front to, forward, right? That means you have empty spaces here. So for each time you move your front or the head forward, you create what? Empty spaces. And there's no way for you to come back to these spaces, right? So that means these spaces are just wasted. Okay, so that is one of the trade-off of using a simple queue. It is very easy to implement, but spaces get to waste, okay, because you can't come back again. You can't bring this front backward again to repopulate all these empty spaces, assuming that this front has moved up to this point. Good. And this is what the next type of queue solves, which is the circular queue. So I don't know if there's any question on the simple queue system. Is there any question? Are we together? Can you guys still hear me? Can anyone hear me? All right, great. Great. So the simple queue system, though, is simple to implement. It's just an array system. Once you add, you move your tail front. Once you remove, you move your head front. But you get to waste spaces because you cannot come back and repopulate those spaces. But the next queue system solves that, which is the circular queue, right? So so look at it. It is also known as the ring buffer. Yeah, like this, though in real life it is not round, it is not circular, but in real life, it's still like your linear queue in real life, okay? But picture it as circular because it works in a circular manner, even if it's like this, okay? So in real life, it's not this circular, but it works in a circular manner, and we'll see how it works. We'll see how it achieves this, circular shape. So now this circular shape is this circular behavior is what actually helps it, is the improvement on the simple queue. I remember that this simple queue, the issue that we had with it is that you cannot come back to repopulate, right? And that is what the circular queue solves. You can always come back to the empty spaces and repopulate, okay? So giving it that circular behavior. So even if you get to the edge, you wrap back, you wrap around. It always wraps around, okay? All right, so it always wraps around the end of the array, and it reuses space efficiently. Okay, so that is the improvement of the circular queue on the simple queue. The only trade-off here is that it is a bit hard to implement. We tend to use more of modulo operator, and if you are not careful, you may run into array out of bound exceptions. But once you understand it, it is very, very sweet, right? But it is still, space constrained, right? It is still, space constrained. In that, if you have not removed any item, okay, and you just been adding, once it gets to the edge, once it gets to the last item, you can't add again. It can only wrap if you've removed something, at some point, that if you have, dequeued at some point. Yeah, so that is it with the circular array. Let's quickly run through this. This is the priority queue. I won't focus much on this in the priority queue, right? Because it's not like the focus of this program. Yeah, so priority queue is more of a, when there's a priority, the top item here is more of, I think somebody raised down, I don't know. Okay, so the top item is always one with the higher priority, and is used for more of urgent tasks. For example, you want to, like, you have more of a ranking system where you process the higher priority task first, so you can achieve that with your priority queue, right? So you can see this this diagram that points to decreasing priority order. All right, so I will just run through this, and yeah, the next one, which is the last one, is the deck. Okay, the deck, in that the rest queues have been you add from the back and remove from the front, right? So the big difference between deck and other queues is that in deck you can add from the front and remove from the front. You can add from the back and move from the back. So most times it gets to serve as both a queue and also as a stack, but it's a bit advanced, right? It's an advanced type of queue, right? So it's not the focus. Maybe on subsequent DSA sessions will go deeper into these queues, but for today, yeah, so for today we'll focus on some other ones which we'll get to see. So these are the queue operations, right? And like we established earlier, all the queue operations, they are constant time operations, right? So we have the enqueue, which is adding from the rear. We have the queue removing from the front. We have the peak. So the peak is just used to view. It's used to view the top item, that is the head, right? We have the is empty. It's just used to check if the queue is empty. Okay, and others like the is full and is size, the size. So these are just like the standard APIs. Like I say, the standard APIs or the standard methods that we tend to implement on queues. Okay, so queue implementation. Okay, like I said earlier, we'll be looking at two ways to implement a queue. Okay, so the two approaches to implementing queue are the array-based implementation and the linked list implementation. And mind you, array-based, this is not array list. Array list is resizable, right? This array-based is not resizable. It has definite size. It is size constrained, right? But it has a better space optimization, actually. Then the linked list implementation, it is resizable, not really resizable per se, it is dynamic. Okay, so if I say resizable, that means that at least it has a size, then it can always increase and decrease. Well, no, like it is dynamic. It can increase, it can decrease, but you don't really set its size initially. Okay, and yeah, it also has its own trade-off. Space management is quite poor on the linked list. All right, so so that we will be going to the code parts, right? So that's okay. I see I have some time, so let me just read through this. I believe most of us, if not all of us, who've at some point used linked list in a task, or maybe on DSA practice sections, you may have used linked list. So that your linked list work with nodes, right? The node, which is yeah, you can see like these things are like node. This is like a value and the next pointer, a value and the next pointer, a value and the next pointer. And that aggregation of nodes forms a linked list, right? So So the linked list implementation of a queue, it uses nodes, right? You can also, it uses nodes, which is your linked list, right? So the merit is that it is flexible and no overflow until memory is exhausted. Unlike the array that you can run into array out of index, but in the linked list implementation, you don't face that until you are out of memory entirely. Okay, which the current systems that we have, the new systems we have, the memories are actually great, so you hardly run into memory issues these days. So the merit is that you need extra memory for pointers, right? You know that all these pointers, they're all pointers, right? These are nest pointers, so you need extra spaces for them, and you have the allocation overhead, right? Okay, great. So let us go to the code wise and look into, first of all, let's let me see what I have here. Oh, okay, great. So let's look into the secular array implementation. All right, so I will just quickly open this. So I've prepared this, right? So we'll just walk through them, and we'll look at each of the methods and run some print statements. Though today we'll not solve any question today, because today is more of an intro into this. So I believe there may be another section to actually solve questions, go deeper into this, but it's more of to introduce these to us, and yeah, we have like an overview of what is going on. Okay, so here, the first part here is the array implementation of a queue. And here I use more of generic so that, okay, you can use this for a string. You can use this for an integer. You can use this for basically any data type that you want. So that's why I made it for a generic. So here you can see this one, this property here, called what? Queue, and it is an array, right? It's an array, right, of this type. So this type is determined at the point that we are creating this queue. We can pass the type that we want. So it has the queue which actually holds the data. Okay, then it has the head, it has the tail, it has the size, and it has what? A capacity, right? Great. So at the point of creating this, which is your constructor, okay, you pass in the capacity that you want. If you want your queue to take in 5 items, 2 million items, whatever capacity you want, you pass that in your constructor. So here it's actually assigns, right? It assigns this, right, to these properties here. So let us look into the NQ, and we'll identify like a critical thing here that makes this a secular queue system. Look at this, right? Though we've not gotten to this part of the code, but just pay attention to this, right? Now, so the first check is more of a protection stuff, right? More of to avoid array out of index exception. So you check if the size is equal to the capacity, your true queue is full. So you can handle this error in any way that you want that fits the program you are writing. But to just keep things simple, we'll just handle this this way. Okay, now yes, where things get interesting. He says that the tail, which is the end, okay, the tail, okay, which is this. Let me show you guys the tail. So I'll just use like a simpler queue so that we can. So the tail is this ray here, ray or the tail, okay. So here it says that the tail is equal to what? Tail plus 1 modulo capacity. So now you know that for each time you add an item, you move the tail forward, right? Are we together, guys? Okay, great.
Yeah.
So for each time you add an item, you move the tail forward, right? Good. But you know that array is size constrained. So if you keep on moving, forward, you get to the end of the array. You get, right? And once you get to the end, how do you wrap? How do you wrap and come back? Okay, so this is what handles that wrapping. So it ensures that this movement, your tail never gets outside your size, your array size. So that is it. So as you move, if there's space at the back, it can wrap. That is, you've moved to the end, and we have the queue at some point, so it can always wrap again and populate that extra item. So I know that this may sound a bit rough at this point, but once you just take your time and go through it, it's quite straightforward, and that is the magic of circular queue. And once you get this, you can basically solve most of the circular queue questions, and you can also apply it in your workplace if you need to, if you need to write. Though most times you don't need to write all these things from scratch. Okay, so this ensures that our detail doesn't go above, outside the index, right? So then it's, it does this array, assignment, the queue at this given index set it to this. So this is where it does that, assignment, that is the storing of the value, and then it increases the size, right? Good. So this is our NQ. Okay. So the next part is the queue. So this is more of what a protection, right? Yeah, best practice, you need to I think it's called a protective program. There is this fancy word that they call it, more of a protective programming or something like that, where you always look out for the various points of failures in your system. All right. So because it doesn't make sense, to dequeue from an empty queue, right? It doesn't make sense, and also it can break the system. Okay, so if the size is 0, it shows this word queue is empty. X, it gets the value, it retrieves the value at that point you want to the queue, and it sets that point to empty. It gets the value you want, right? And it sets that space to empty so that more things can come back to it. Okay, now you know that when we enqueue, we move the tail forward, right? Now, when we dequeue, we move the head forward. Okay, so here is where you move the head forward, and this is also what ensures that as you dequeue, the head doesn't go out of the index. So it's why you always have this. It's more of index plus 1, modulo capacity. So this ensures that they always wrap. So as you dequeue, the head will always wrap back. So that is why it's a circular array. So be that even though it's sequential, like on a straight line, but it imitates the circular movements using this. So this and this, right? And this. So they are what ensures that that circular movement. So once you dequeue, you reduce the size. Okay, basically that is it. Okay, and peak, peak, we'll just say peak is just to view the top value. Okay, and your top value, peak is just to view, like peak, like when you peek into something, right? So it's just to view, at that point, that the current processing, that is where your process, that is where your head is. The head kind of signify the stage or the point you are in your processing, right? So peak is more of to view it. Good. So So I know that this is more of talking and code display, right? But to save time, we just need to, yeah, do this. So I've arranged, I've added some log statements. I know that we established that queue is a first in, first out, right? First come, first serve. So I've enqueued this 3, 1, 6, 5. So the behavior that we want is that once I run this print statement, I should see 3, 1, 6, 5 in this order, right? So let me quickly run this. So we'll see how we got 3, 1, 6, 5 in that order, because it's what a first in, first out. So that is it on circular queue implementation. And mind you, it is space constrained, okay, but it is very, very efficient, right? So is there any question in space in circular queue implementation? If there's no question, I'll go over to the linked list queue implementation. Okay, so that we quickly run through it and we take questions and still maintain the time. Okay, so here is the linked list queue implementation. And if you watch, you can already see some striking difference, okay, between the linked list and the circular queue. Okay, so here we maintain that is an inner class, right? Okay, so you can make this an inner class. You can also make this an a standalone class on its own. But most times it just makes sense to make it an inner class since it's part of the entire flow. Okay, so we have like a node class which contains the data and the next pointer. And mind you, we say that one of the trade-offs of your linked list implementation is that you need to maintain an extra space for the next pointer, right? All right, so you have this inner class, you have the data which stores the value you want. And also I made this a generic, so you can use it for any data type that you want, anyone. Okay. All right, so here we have outside this node class, which is the inner static class, right? We have these two definitions, the head and the tail, right? The head and the tail. That is just the two definitions that we have. And mind you, you know that linked list links that are linked to each other using the next pointer, right? The head has a nest, right? So the head uses the nest to point to the node. The next node uses the nest to point to the node. So it's more of pointer, just as we showed in this place. We showed here that it's more, you can see this nest pointers. So I believe we all know what a linked list is all about, so I don't need to go into the nitty-gritties of a linked list. All right, so still, similar concept that we talked about in the circular queue, right? So I kind of use the circular queue first because it's a bit hard to understand. And once you understand the circular queue, then the linked list queue is just a walk in the park, right? Very, very straightforward. So still the same APIs, the enqueue and the dequeue, right? Same APIs or same method, okay? All right, so if you want to enqueue, first you create your node, right? You create a node and you check, is it empty? Basically, this method for empty is just checking, look at, is the head equal to null? Okay, so if it's empty, you throw that queue is empty, right? Sorry, if it's empty, sorry, I thought I was here. So if it is empty, you attach the new node that you created to your head, right? Else, you attach that new node to the tail next pointer, and then you move the tail to that new node. Same concept of linked list, right? So once you get how linked list function, it's still same concept, right? Linked list is basically a queue system. So there's no much thing to talk about here, right? Linked list is just basically a queue. So this is the same thing that you do in a linked list implementation. All right, so the next part is the queue. Okay, so almost same thing you have in your linked list, so you get a value and you set that space, and you move the head to the front. mind you, look at this, look at this. When you add, you move the tail to the front. That's why you say tail equals what? New node. So you move the tail to the front. Now here, when you do the Q, you move the head, to the front, right? Good. So it's why you say, head equals to what? Head dot next. So you use it and move to the next node. Okay, so here is still the peak. The peak is just to get what is at the head. That is your current, processing. Okay, and here I've, made some log statement and similar behavior. Here, let me just show this. I know I missed it out at the other one. So I've initialized a linked list of type integer. Okay, yeah, of type integer, and I've enqueued 4, 5, 6, 7. So the behavior that we want is that we should be able to to get 4, 5, 6, 7 when we work with the queue, right? Good. So let me run this quickly. So still 4, 5, 6, 7, same behavior. So you can see that both the implementation of a circular queue and a linked list queue, they are pretty much same thing, right? And if you want to make it more advanced, you can have like maybe an interface, just as you have in Java, an interface that has the enqueue and the dequeue and the peak, just those methods, and you can now use it to implement your circular queue, your linked list queue. You can take it further, but that already has been done, right? That is it. So they are quite straightforward implementations, and straightforward and powerful, right? So let's continue with the slides, and let's continue with the slide. Okay. Yeah. So I think this is, well, I've looked through this. We've seen how this functions, that it is fixed capacity. And one thing with the fixed capacity is that you can easily run into array out of index, but we handle that nicely, right? We handle that nicely by checking, okay, is the size within, is it more than, is it less, and we handle that nicely. Okay, so you should always watch out for that. If you're using circular queue or simple queue, sorry, if you're using array implementation because of the fixed size, right? So you should always watch out for that overflow. Okay, so like I said earlier, the circular queue is still like your regular array, which is sequential, right? It is sequential, right? But it behaves like a circle, right? It behaves like a circle, okay, because of that wrapping over that we had, that index plus 1 modulo capacity. So that wrapping over is what helps it to that always come back more of a circle stuff. Okay, but on a real presentation, it is straight line, not circular. All right, the summary. Okay, a queue is fundamental data structure that follows the first in, first out principle, where elements are added at the tail and removed from the head, making it ideal for ordered processing in systems like task scheduling and buffering. While a simple array-based queue can waste space, like we saw, as elements are removed, the circular queue improves efficiency by reusing freed position through modulo indexing. We saw the modulo operation indexing, right? Eliminating the need for shifting and ensuring optimal memory usage. Overall, yeah. Queue operations such as enqueue, dequeue, and peak run in constant time, making queues a reliable and highly performant choice for managing sequential tasks. So that is all from me. All right, Mr. Sam, you can take over. Can you hear me? So is there any question that anybody want to ask? I will see have like 10 minutes for questions. If you have any question, you can just ask. I can't see the person raising. So any question? Are you there, Mr. Sam? Are you there, Mr. Sam? Hi, Mr. Sam. Is it there? Okay. So I believe Mr. Sam is not here to coordinate the questioning parts. Okay. So, all right, go ahead. Somebody wants to talk.
Oh, all right. I wanted to reach out to Sam, but maybe I'll kind of sit in for him.
Okay, go ahead. Go ahead. All right, great.
Great. Yeah. So please, anyone in the house have a question, please do go ahead and ask a question. Mr. Bright is here, strong and ready to pick up questions. So do feel free to kind of throw in your questions. The one thing is clear, like no question is like don't be shy to ask a question. So don't think, okay, my question may not make sense. Even if it doesn't make sense, I think that is the question we are looking for. You can just throw it in so we can look into it. All right. With that, if we don't have questions, it means Mr. Bright did a marvelous job by walking us through the queue and so I guess everyone, I believe that everyone kind of understand what has been taught in the section. So at this point, I would want to know if Mr. Bright has anything else to add up before we finally call it a day.
Yeah, so from my end, you see that we didn't really solve like a DSA question. So maybe we can always reschedule like for the part 2, right? Yeah, the admin can look into that. Maybe later, much later, we can reschedule for part 2. To like solve questions. To like solve sample interview questions that involve Q. So today is basically to like introduce the whole Q system, the whole ideology of a Q. I know, already know about a Q, right? But just like to introduce the different types of Q that we have and the ways to to implement them to the team, right? Then next time we'll go deeper into solving DSA questions. Yeah, thank you.
All right. With this, I would say, Mr. Bright, you, sorry, you did a very wonderful job because I believe most of us here, although we might have some seniors in the house, I believe we also have more of the upcoming ones who truly need this very explanation. So I believe starting at this point really makes sense. Then we can kind of look into the upcoming, probably the part 2, where we'll get to kind of start solving problems. But with what we have done so far today, I believe it lays a foundation for the upcoming section, which we might kind of want to solve problems. So with this, I will say thank you very much, Mr. Bright. Thank you for your time, for your wonderful presentation and the visuals that were used in the slides. truly is not easy making our time to prepare this. So I'm very much grateful, and we, the NAIJA-JUG family, appreciate your time and efforts that you have put in making this program a success. We also appreciate everyone present, all our NAIJA-JUG team members, the people who are doing the boot camp, and every other people who have joined in this DSA section this evening. I say a very big thank you to everyone. Do have a wonderful evening from here. Um, at this point, I will say goodbye from here and do enjoy the rest of your day.
Bye bye.
Right, bye. All right, bye everyone. See you all in the next section.